Welcome to this forensic analysis of the Hurricane Ian flood event along the Rouse Road corridor in East Orange County, Florida. What you are watching is a precise elevation animation built from high-resolution LiDAR survey data. Each colored band represents a specific ground elevation, measured in feet above sea level, using the North American vertical datum of 1988. We will animate the floodwaters rising from the lowest elevations up to the peak flood stage of 51.1 feet that occurred on September 29 and 30 of 2022. The deep blue colors you see first represent the little Econ River channel itself. This river flows northward through the study area, passing under University Boulevard before continuing toward Seminole County. The channel bottom sits at around 30 feet elevation in some locations. As we add elevation bands, you can see the river corridor widen and the adjacent wetland systems begin to appear. These wetlands are hydraulically connected to the river. When the river rises, the wetlands fill. When the river falls, the wetlands drain. They function as one integrated system. Now we are entering the critical flood zone between 50 and 53 feet elevation. Notice how the animation slows down here. We are showing tenth of a foot increments in this range because small elevation differences matter enormously for flood impacts. A property at 50 feet elevation experiences 1 foot of flooding when the river reaches 51 feet. But a property at 43 feet elevation experiences 8 feet of flooding at that same river stage. The colors shift through the turbo spectrum as we approach the peak flood elevation of 51.1 feet. At 51.1 feet, the flood pool extended across Rouse Road and deep into the wetland lobe east of the roadway. This was the maximum water surface elevation recorded during Hurricane Ian at this location. The river held at or above 50 feet elevation for over 34 hours, from 8 in the morning on September 29 until after 6:30 in the evening on September 30. Residents had no warning. The rain had already stopped hours before the peak flooding occurred. This was backwater staging from a choke point to the north, not direct rainfall runoff. Now we switch to a depth of inundation visualization. This map answers the critical question: how deep was the water at each location? We calculate depth by subtracting the ground elevation from the flood elevation of 51.1 feet. Anywhere the ground is lower than 51.1 feet, we show the flooding depth. The colors progress from bright yellow at shallow depths of 1 to 2 feet, through orange and red at moderate depths, and into deep purple and blue for the most extreme flooding exceeding 15 feet. The shallow yellow zones represent areas where flooding reached 1 to 3 feet deep. This depth damages vehicles, floods ground floor units, and makes roads impassable. But it is survivable if you stay out of the water. The orange zones at 4 to 6 feet deep represent life-threatening conditions. A person cannot stand against flowing water at this depth. Vehicles float and become death traps. The red zones at 7 to 10 feet indicate complete inundation of single-story structures. Everything at ground level is destroyed. The deep purple and blue zones show flooding depths of 15 to 21 feet. These areas correspond to the Little Econ River channel and the lowest portions of the adjacent wetlands. 21 feet of water is the height of a 2-story building. The entire river corridor became a massive lake stretching from Rouse Road westward toward the natural river channel. Flow rates through the system exceeded 10,000 cubic feet per second, overwhelming the river gauge at Michael's Dam. The gauge was unable to measure flows beyond its design capacity. Understanding why this happened requires looking at the watershed. The Little Econ River drains over 88 square miles of heavily urbanized land. All of that runoff must pass through a constricted reach of the river north of University Boulevard before dropping sharply into Seminole County. When intense rainfall generates more flow than this choke point can pass, water backs up. A pool forms south of University Boulevard, and that pool rose to 51.1 feet during Hurricane Ian. The apartments and homes in this area were inundated not by rain falling on their roofs, but by river water backing into the connected wetland system. What you are now seeing is actual footage from the Orange County Sheriff's Office helicopter, recorded between approximately noon and 12:15 on September 30, 2022. The floodwaters had been rising since early morning, By the time this helicopter arrived, vehicles were completely submerged in parking lots. Only their rooftops remained visible above the brown floodwater. Fuel and oil sheens spread across the water surface. Ground-floor apartment units stood flooded to their windowsills. Residents who had not evacuated were trapped on upper floors. The helicopter footage reveals the true scale of this disaster. Looking south along Rouse Road, you can see the water extending for hundreds of yards in every direction. The road itself is underwater. Emergency vehicles could not reach the area by normal routes. Some residents attempted to drive through the flooding, and their vehicles stalled and flooded. Others waded through chest-deep water carrying children and pets. These ground-level photographs and videos were captured by residents throughout September 29th. In the morning, water was rising around vehicles in the parking lots. By noon, those same vehicles were submerged to their rooflines. By afternoon, only scattered rooftops and antenna tips marked where cars had been parked. The water continued rising even after the rain had stopped many hours earlier. This confused residents who expected flooding to recede once the storm passed. Instead, the river was still collecting runoff from 88 square miles of watershed and backing it into this low-lying area. The flood did not begin receding until late on September 30th, and even then the decline was painfully slow. River stages remained above 50 feet until after 6:30 that evening. Many areas remained flooded for days afterward. The ground was saturated. Stormwater systems were overwhelmed. Additional rainfall in the following weeks delayed recovery further. Mold began growing in flooded structures within 48 to 72 hours. Contents that had been submerged were total losses. The cleanup would take months, and for many residents, recovery would never be complete. What you have witnessed in this video is not ancient history. Hurricane Ian struck in 2022. The conditions that caused this flooding have not changed. The watershed is still 88 square miles of impervious urban development. The choke point north of University Boulevard still exists. The wetlands still connect directly to the river, and storm intensities are increasing across central Florida. The published FEMA flood elevation of 45 feet for this area is dangerously wrong. The actual flood exceeded that by more than 6 feet. Until accurate flood information replaces the flawed federal maps, residents and property owners in the Rouse Road corridor remain at serious risk of another catastrophic flood. The relic shorelines in the Orlando area are defined by these elevations, and their ages based on current science is estimated in this table. The plus 28-foot shoreline represents a sea that was in the range of plus 20 to plus 25 feet above sea level, with hurricanes of that time being categories 7 to 8, pushing surge and waves 8 feet above the sea level to cut the shorelines we see today. The very prominent shorelines in the Orlando are at 28 and 100 feet above sea level, and the next most prominent shoreline is at 70 feet above sea level. Orlando itself is just above the 100-foot shoreline and rises to about 125 foot above sea level. The narrow ridges off the old 100-foot shoreline are linear ridges, which are in the range 70 to 100 feet above sea level, and the one of interest to the Little Econ River we call the University of Central Florida Ridge, or the UCF Ridge. It separates the Little Econ River from the Big Econ River, both of which flow northward, and then join and flow east to the St. Johns River. Another shoreline, which is more subtle, is at 42 feet above sea level, but it seemed to be a pause as the sea level retreated. These shorelines were developed sequentially from high to low elevation. The Orlando metropolitan area has the most complicated drainage system in the world, which is still evolving. Geologically, the land above elevation 70 feet above sea level is landlocked except for the UCF Ridge, which is off the mainland. All of the lakes at these higher elevations have no natural outfall and have flooded since Orlando started developing in about 1845, and the flooding has been mitigated using drainage wells which let the surface water drain through large diameter tubes into the underlying Floridan aquifer, which is 100 foot below land surface and contains groundwater at a pressure much lower than the lake levels. These drainage wells have been used since 1903, but their reliability is not robust enough to prevent flooding. From the time of reconstruction in 1875 to present, the higher ground, which has no natural surface water outfall, has been altered by cutting drainage ways to allow the water to flow out to the St. Johns River on the north and east, or the Kissimmee River on the south, or to Lake Apopka, which now has a channelized outfall to the Ocklawaha River. The Little Econ River cannot naturally handle the drainage area which is now connected to it, and has allowed Orlando to be developed. It is one of 3 northward-facing bottlenecks, which includes the Little Wakiva River and Howell Creek. The Little Econ River has a well-defined bottleneck to flow, as shown in these animations that follow, and flooding occurs upstream of these bottlenecks. There are bottlenecks in the southward flow also, but not as severe as the Little Wakiva River and the Little Econ River, which flash flood. Both of these are urban canal systems which have flooded residential structures regularly since 2017, when rainfall intensities increased in Florida as the Gulf of America has become much warmer. Look at the detailed configuration of the land, and we can now see how it was formed. The topography is key to understanding the drainage. The animations show the Little Econ River on the original statehood plat of 1845, which would represent mapping of the flowway in its natural form, before heavy equipment was available to create major drainage alterations. The 1890 map of Orange County is a rare true survey of the area when Orange County and Seminole County were not yet separated. However, by 1890, major drainage changes had already started in earnest, and it shows the first iteration of alteration, which predated the major modifications which were made in the 1900s, especially after 1955, when the space industry led to a boom in Orlando. The neck in the Little Econ River is a natural neck between 2 ridges, and it was crafted by nature for much lower flow rates than the 10,000 cubic feet per second we see today. Understanding the complicated topography of the land shows that both the Econ River and Little Econ River are swales between old beach ridges, and the constricted flow channels were intended for much lower flow rates. These high-resolution topographic animations show the ancient sea levels, especially at 28-foot elevation, and the 42-foot elevation, which are important for the Little Econ River as it rises up to elevation 50 feet above sea level. These ancient shorelines create ridges and swales between the ridges, which can be seen with the colorization. The Little Econ River is bounded on the east by the University of Central Florida Ridge, which runs north to south and is between elevation 70 feet to 100 feet above sea level, and it was offshore from the main Orlando Ridge to the west. The river channel forms a very narrow neck north of University Boulevard, which chokes the discharge at that point. It is a natural constriction not capable of handling flow rates as high as 10,000 cubic feet per second, and it has been a problem for Orange County since the 1950s. These topographic elevations in living color show the landscape limitation very clearly, such features not being obvious at ground level. The United States Geological Survey quadrangle maps from the 1950s are shown, and they illustrate the neck-like shape in this part of Orange County, which is a bottleneck. This USGS topographic map was prepared in the 1950s and representing land surface before development. Hurricane Ian dumped over 13 inches of rain on the Little Econ watershed in less than 12 hours. Flow rates at Michael's Dam exceeded the gauge capacity, peaking at an estimated 13,000 cubic feet per second. The river stage rose from 43 feet to nearly 53 feet, overtopping Rouse Road and flooding the adjacent wetlands. The rain stopped by 9 a.m., but water kept rising for hours as the massive watershed drained through the choke point north of University Boulevard. What you're seeing is Sentinel-2 satellite imagery precisely mapping Hurricane Ian's floodwaters across central Florida. This flood mapping technique was developed right here in Orlando, born out of necessity during one of the most destructive storms in Florida history. It's one of the few positives to emerge from that disruptive event. Since Ian, this method has proven remarkably precise at capturing flood extents across Florida whenever the satellite passes overhead in cloud-free conditions. What once took days of ground surveys can now be mapped from space within hours, giving engineers, emergency managers, and communities the accurate flood data they need.